off we go. So yeah, let's finish these. So we talked about qualifiers. That's just ways to like soften the things you're trying to say. Like sometimes it's true, not almost always it's true. It's not like black or white. It's not like all or none. Usually, we learned how to specify ideas like that in our quantifiers, like a for all there exists. So there exists is kind of like the mathematical equivalent of sometimes, which is cool. And yeah, we learned how to specify some fun things. And this kind of stuff that we were doing before is essentially like we're making a statement in math that everybody can understand, but it's not like we're saying it's true or false yet. We're saying like we're putting it out there, and now we can prove it true or false. So it's like a theorem statement. We can prove it or disprove it, and so we still need to have a proof. Like this is a true statement, this thing that we wrote, but at least and like now it's able to be proven. It's not yet proven true yet. Okay, that's the idea. So yeah, what I want to do today is go full circle. Let's translate like an idea from English to the math with our quantifiers and our logical connectives and all our fun things like that. And then one way to prove that your logical statement involving quantifiers is correct is you could write a program. There's a really cool correspondence between programs and proofs, which is very powerful, that you might learn about in grad school one day, that I want to show you a little sneak peek of. So let's do that. So let's remember some terms. So first of all, there is a term called a predicate. That's going to be useful today. So a predicate is just a proposition with some variables. So a proposition is the word we know already. Okay, that's just a sentence. It's a statement. It's something that is true or false. All right. So a proposition is a statement that you can make, something that is true or false. Not both, not neither, right? So like a proposition is like it's raining today. That is a proposition that you can either prove or disprove. If we asked this like last week or something, maybe it was true, but this is now a false proposition, right? It would be true if it were raining today, though. Right? So it's something we can prove true or false. And a predicate is a proposition with some variables. So it's not yet true or false. It needs some variables filled in. All right. So here's a predicate definition. It kind of looks like a function. So let's define the predicate P on a variable x. P of x, let's define that to mean that x has a cat. Okay, does that kind of make a little bit of sense? So like this is a statement, this predicate, it's a proposition with a variable in it, at least one. There's the variable. Do you see how this isn't true or false yet? It depends on who x is, yeah? So I have a cat, so like you can plug me into P. P of Lawton is true, right? But maybe you live in an apartment that does not allow pets or something, and so maybe it's false if you plug yourself into this predicate. So you need to like replace all the variables with concrete things before the predicate becomes true or false. All right, so that's what a predicate means. It's a proposition with some variables. You can plug in stuff for those variables, and it might be true for those, might be false for those. It becomes a proposition the second you replace the variables. Okay, and the reason we're going here is because all of our quantified statements, they introduced a variable. Every time you use a quantifier, you introduce a variable. And so like here's an example of using a quantifier with our predicate P. So I can say, for all x, P of x. What is this trying to say? This is saying like, all right, for any possible x that you plug in, I'm claiming that P of x is true. All right. So what does that mean for our predicate x has a cat? This is equivalent to me claiming that everyone has a cat. Do you see that? Everyone has a cat. That's what that means. For all x, P of x means x has a cat. For every single x, P of x I'm claiming is true. Therefore, this statement means in English, everybody has a cat. Can you see how I'm doing that? If you change this to there exists an x such that P of x is true, you're saying that at least one person in the universe somewhere has a cat. That's the idea. Okay, so that's a predicate, and they're going to be useful combined with our quantifiers. All right, so this is going to help us like take what we want in English. We want to say something very precisely. We've got to get it out of English first, and then we can go and prove it. All right, so I'll try and answer that. So here is my first example for the day. It's gonna take a while. So, all right, this is a statement that you can make, right? There is a prime number that is greater than 50. That's a total statement that you can make. That's a true or false thing, right? It's either true or it's false. I'm pretty sure it's true, right? I'm pretty sure there is a prime number that's bigger than 50. There's an infinite number of prime numbers. So let's specify it. Let's mathematically specify what it means, all right? Because then we can prove it true or false. Let's change this sentence into math. That's where we're going, right? First step. So, all right, there is a prime number that's greater than 50. So if this is true, what can we claim about that number? So let's give it a name. Let's call that number x, and we need to ask now, what is true about x, okay? X is like the prime number that's greater than 50, right? There's two things true about it. It's greater than 50 and it's prime, yeah? So those are the two things that are true about that number x, if this whole statement about it holds, yeah? And so this is more like math, right? X is greater than 50 and x is prime, like this and, you can change that into logical and. That's getting a lot closer to math, yeah? What is this, though? What is this sentence looking like? It looks like something with a variable in it. So this right here, this is a predicate. You see that? A predicate. Aha. So, okay. That means if I find one good value for x, I've found a value that's true for that predicate now. It's like p of x. Define it to be that this is true. Interesting. All right, we can make this more like math. Let's pretend like x greater than 50, that's like mathy, that's already good. But like prime, x is prime, that's still English. Let's change that to this. Let's say prime of x. That is itself a smaller predicate. So you can ask for whether or not something is prime, and let's say that gives back true or false, depending on what you plug in. Right? So like prime of 5, it's like mathematical code. Prime of 5 is a predicate that's true, right? You can prove that true. That's a true statement. But prime of 6, if you plug in for the variable you're asking about, that's totally false, right? Because it has 2 and 3 as factors. So that is itself a predicate. So you can build up predicates using smaller ones itself. A predicate. Interesting. And if you think about it long enough, greater than is also a predicate. It's like depends on x, right? Whether or not it's true or false. That's kind of cool. So that's a lot closer to math now. And so what do we want? Like our goal is to find some value of x for which this is true, yeah? Because that will prove that there is a prime number that's greater than 50. If we can find a good value for x, we're happy, right? And this is true about x. So that's our goal right now. If we can find some x value, and you'll see this abbreviation a lot in math, it just means such that. If we can find some x such that all this stuff is true about x, then we're happy, all right? So before I scroll down this thing in bold, you see that there's a quantifier there. So we can find some x. If there exists an x such that that is true, we're happy, okay? So bringing it all together, what do we want? What do we want to prove? How do we translate this to math? We want this, right? We want to know, hey, is it true that there exists an x such that x is greater than 50 and x is prime? Okay? That is the idea now. So the second we've added the quantifier, like this could be true or false, depends on the x, right? If you choose x being 20, I don't know, 23, I think that's a prime number. So it's prime, but it's not greater than 50, right? So like it's not true. Depends on the x right now. This is a predicate, but the second we add the there exists bit, it kind of quantifies over every possible x, in a sense, even though it's not a for all. It lets us translate from a predicate back to a proposition, because this is now something that's true, right? This is a true statement. True statement. That is a proposition, right? And the addition of that there exists quantifier made all the difference. So now this, like reading it all as one, there exists an x such that x is 50 and x is prime. That's true, right? Because you can plug something in for x and make that work. Like 51 maybe. Or no, 51 is divisible by 3, so maybe 53. So yeah. Every time we have a quantifier, like we had, this was a predicate, we added a quantifier and that turned the predicate back into a proposition, which is very cool. It's like, this like got rid of the x in a sense. It declared it in code, in mathematical code. So yeah, the new key thing, the idea behind quantifiers is every time you use a quantifier, it's essentially you creating a variable. It introduces a brand new variable, and you're quantifying over it. That's the idea. So it's a helpful way to take a predicate and ask something about the predicate that you can then go and prove. It's like, this depends on X, but now this is something you can prove true or false, right? It's a good way to go from a predicate to a proposition. All right, so this is some complicated topics for the day. These slides are a little weird, but hopefully that makes a little bit of sense. Any questions about, like, this is a predicate, has a variable, we don't know if it's true or not. But this now, we're quantifying over that variable, and now it becomes a true statement because there is a prime number that's bigger than 50. And that can be filled in for X. There is one. There exists at least one that'll make this true. So now it is now we can create it to be true. Beautiful. All right, so how could we prove this true, right? Now our goal is, like, how could we prove this statement to be true? Because I think it is true, right? Or maybe you don't know. So all you have to do, right, to prove this true is to, like, try a bunch of X's. Find one good one. So just, like, go through a bunch of numbers bigger than 50 and look for the primes, right? You can make a program for that. So that's us coming full circle. We can go from the idea of a proof to making code to prove that something's true. It's really cool. So, okay. So yeah, we can make a program for this. What is our algorithm, right? What's the algorithm that we can use? All we have to do is search for a prime number that's bigger than 50. We can totally write a program for that, can't we? So assume that we have, just like we need a prime predicate, assume we have like an isPrime function. That's not in the standard library, but we'll make one. That tells you, like, when something's prime or not. So, like, isPrime, it returns a bool. So, like, if you call isPrime on 42, that'll return back false to you. But if you call it on, like, 5, it'll return back true. And so, like, what's our strategy to find a prime number that's greater than 50, to prove this predicate true once and for all, to find a good X value? Well, it's kind of like, what if we just start, right? What if we just start looking at the first number that's greater than 50? Look at 51. Is it prime? Look at 52. Is it prime? If it wasn't prime, keep trying. Look at 53. If it wasn't prime, keep trying, right? And the second you find a prime number, you can stop because it was bigger than 50 when you started. Does that make sense? So that's you proving something with code, which is very, very powerful. Very, very cool. So, like, yeah, we can just iterate. How do we go through a bunch of numbers? We can make an iteration variable. Make it called I or something. You can use a loop. Start it at 51. And just, like, keep advancing it. Make it 52, make it 53, as long, and just keep checking if I is prime. See that? That's going to be our strategy. That's going to be the code. And so here's what's called pseudocode. It's English-looking code that describes an algorithm. It's not actually Python or anything, but you can easily make it Python. So what do we got to do? It's like, here's what we need to do to prove our quantified statement to be true. What we need is to go through all the numbers, like with the while loop, starting at 51. Potentially, this could run for until the end of time if there is no number that's prime that's bigger than 50, right? If it never stops, then maybe it's a false statement. But we can discover it being true if we find a good value, right? So go through each number, call them I, and then if I is prime, we can stop looking. Then we're good to go, right? So either, like, there's a quit function in Python that we can call that stops our program. We can print stuff out. That's going to be our goal now, all right? Because if this loop ever finishes, it will find something. If it never finishes, well, then we don't know if it's true or false. Maybe there's, like, a giant, giant number that we just have to wait a few billion years to find. But this is a good strategy, okay? So we're going to write a program, and that's going to, if it prints out something, it'll tell us that the thing was true. Very, very cool. Very, very powerful. So let's see here. Dun, dun, dun. Let's make it's one of those rare non-code plus code days. So let's go to idle. I'll write a program to do this. And let's see what is today's lecture number while that's opening. We're lecture 21 today. So I'll make a new file after I make this a bit smaller. And I don't stop the projector. There we go. So I'll make a new file, and what should I call it? So it's a file that's going to prove our thing, hopefully. This is lecture 21. Boop. I'll call it prime greater than 50. All right, so here's our strategy, right? What we need to do, here's our code. I would like to loop through numbers starting at 51 and see if it's prime. I'll just assume I have an is prime function that'll tell me if it's prime or not. I'll just assume I have that at my disposal. And so here's kind of what I need to do. I need to start a variable at 51. I'll call it I. All right? And then just forever, potentially until the end of time, while true, forever loop, I would like to look at I. See if I is prime. Check if I is prime. If it was, then like print it out. If it is, print it out and stop the program, because otherwise, like, it's an infinite loop. It'll never stop. Otherwise, if it wasn't prime, keep searching, because maybe the next one is. Otherwise, increment I. Right? Make it 52. Make it 53. I know that you know, right, that every even number is not prime. So maybe you could add 2 instead of adding 1 each time. Just only go through odd numbers. That would save you half the trouble, maybe. But we'll do it lazily. So if we get here, let's see. Otherwise, yeah, if we're here, it didn't work out for this particular value of I. So we'll increment I and like check the next one. Increment I so that we can check the next value. Okay, so that's going to be our strategy. We get to assume we have is prime to do this checking. So it's going to be an if statement, right? So if is prime of I gives back true, then I can do stuff. That means it was prime, right? That's the idea. So do stuff. I do want to say something right now. Checking this is kind of redundant because the if statement, like, it runs its body if the result is true. So this equal true thing is kind of unnecessary. See that? I can get rid of this. It's like if is prime of I becomes and gives back true, that'll make the whole thing true and run the body still. So it's kind of redundant. So it's kind of cleaner to read it like this. If I is prime. See that? If that results in true, I'll run my body. So what do I want to do? If it's true, I want this part. Oops. That. So I would like to print out I because I want to know which one was the good one. That was my value for x. That would make everything work out. And then I also want to stop the program because otherwise it would just continue forever. There's a quit function in Python that stops the program. It's not part of any library, kind of like len. It just exists and that'll stop our program. Stops the program. Okay. So that looks like a good thing to do if it's prime. Otherwise, we got to keep going. Maybe if it wasn't 51, maybe it's 52. It's definitely not 52, so we got to try again and then make it 53, 54, 55 until we find one. So I equals I plus 1. Okay, that's going to be that's a good start. Are there any questions about this strategy and why this code, if it ever stops and prints something, it will have proven this proposition to be true? It's a lot of steps there. Well, we can write a program that proves this thing, which is very cool, very powerful. All right, so now is prime sadly is not part of the math library, at least last time I checked. So we're going to make our own is prime function. I haven't told you how to make functions yet, so you can look away if it's too scary. But I'll tell you soon about how to make your own functions. This is me like giving you a sneak peek. All right, so we need to make an is prime function, and we have to come up with an algorithm to give back true if a number is prime and false if it isn't. All right, so let's plan this out. What does it mean for a number to be prime? How do we check that? So a number is prime when it has no factors other than 1 in itself, right? That's kind of the idea. So a number n, go on Wikipedia, search for what it means to be prime. This is kind of it, right? A number, call it n. We say that n is prime when what's true about it? When only 1 in itself are the things that go into it, right? If there's anything else, that means if anything else goes into it, if n is prime if, or when, if you try any other factor, any other potential factor, it doesn't work out. Like if you try 2 and 3, all the way to like n minus 1, everything that's not 1 or n, if those don't divide in properly, right? If those aren't factors, those don't divide cleanly, with no remainder, right? Into n, and that is actually going to be the secret to implementing this. We're going to check for remainders. We're going to loop through all these numbers. Like if, let's say we're asking, is the number 51 prime? All right, we're going to call that. If n is 51, for example, we want to try 2, 3, 4, all the way to 50. We want to try to divide all of them into n. Right? We want to try to divide 51 by 2, 51 by 3, and check if it was actually a real factor, if it went in. So the way you check that is with the remainder calculation. Does that make sense? So like 51, if you check for mod 2, that give you the remainder after dividing by 2, that gives back 1, because it really, 2 is not a factor, right? It doesn't go in cleanly. There's 1 left over. But 51 mod 3, look, it goes in a certain number of times, because 5 plus 1 is 6, right? That means it's divisible by 3. So this will go in cleanly, and that means I'll get a remainder 0 here. And that will be my proof to show that 51 is not prime. You see that? If it ever goes in cleanly, if a number other than 1 in the number goes in cleanly, which means trying to divide gives you no remainder, that means you found a factor. All right, so let me try and prove that to you. Like 51 mod 2, in the REPL at least, that's 1. 51 mod 3, that really is 0. So we can stop and say, no, 51's not prime. But if you get through them all, then you know, like, that it was a prime number. Like 7, for example. For 7, you got to go through 2, 7 mod 3, 7 mod 4. There's always something other than 0 left over. It never goes in cleanly, because 7's a prime number. There are no factors. 7 mod 6. See how all of those had remainders other than 0? That means those numbers didn't go in cleanly. There was a remainder. If there wasn't a remainder, that means it was a multiple of that number, like 42 mod 2. 2 goes in cleanly. There's nothing left over. So it was a factor. All right, you see how the correspondence is happening there? So that's going to be our algorithm for checking if a number is prime. And so we're just going to loop through those numbers, 2 through n minus 1. We can do that with a while loop, and check this modulo thing. If it ever becomes 0, it was a factor, and darn, it wasn't prime. Otherwise, if we get through all of them, and none of them worked, then it was a prime number. All right, so that's going to be our algorithm. And so I will do that quickly. You can look away if it's too scary, but here's how you make a function in Python. All right, here's how you do it. I'll show you this in depth later. But if I want to use it down here, I got to make it up above. And so here's how you make a function in Python. You say def to define a function. You say is prime, give it a name, and then you give a variable, the thing that you're calling it with, because we want to call it with one thing. And I want to call that thing something. I'll call it n. All right, so this will give back true if n is prime and false otherwise. All right, so then I give a little I give a colon, I indent. So I'll tell you all about this later, but this is like a good sneak peek. All right, so what I want to do to this n value, whatever it was, if it was 51 or 42, whatever, I want to try to divide by 2, by 3, all the way to by n minus 1, right? And check, right? Check if it divided cleanly, right? And that's the goal. So I want to loop through all these numbers. I want to loop between 2 and n minus 1 using some variable. I've used I down here. I could use I again if I wanted to, but I'll use j this time to give us some practice with that. All right, so let's start j at 2. That's the first number I want to loop through and try to divide. And I'll say while j is less than or equal to n minus 1, do something with j, and then j equals j plus 1 to try the next one. So this will loop between 2 and n minus 1. See that? That's perfect. Those are all the numbers that I want to make sure are not factors, because if they are, that means it's not prime. And so what I want to do now is try to divide. Maybe the number n is 51 and j is 3 right now. I want to try to divide that 51 by 3. Try to divide n by whatever j is. Okay? And so check if it went in cleanly. You're going to do the modulus. All right? So if n modulus j, if you try to divide n by j and check the remainder, if that remainder is 0, that means j divided cleanly into n, and it wasn't 1 or that number. It was something else. Right? So j, if this is true, if we get to the body here, j must have divided cleanly with no remainder, right? Remainder 0. Divided cleanly into n. Therefore, j is a factor of n. All right? And the second I find a factor, I want to yell back, whoever asked me if this is prime, no, the answer is false. So the way you do that in a function is you say return. I want to return false back to whoever called me. Okay, I'll tell you all about this later when we talk about functions, but that's a good start. And so here it is, trying the loop. If it ever finds a bad value, it'll say no, false. It's not prime. But things like 7, for example, you get through all the numbers, like this loop will complete and never give back false. Like this loop will be done. We get down here after the loop. If we ever get here, right? If we ever get here and we didn't say no already, that means they all checked out. Nobody was a factor. Nobody that could have made it not prime was a factor. So it really was prime, right? So if we got here, if we get here, down below, right here, that means there were no factors. It was prime. And so we'll say, we'll yell back, return, true. It was a prime number. Okay, so that is going to be the secret there. And yeah, you don't have to look at the function part, but like this is what it means. If you have a number called n, this is what it means to check if it's prime or not. Try all the possible factors, and if anyone ever goes in cleanly, you know it's not a prime number. Okay, so that's a fun little example, and yeah, remember what our goal was. We're trying to prove this this proposition to be true. We need to show that there does exist a number that is bigger than 50 and is prime. We'll call it x. I guess we're calling it I down here. All right, so if we ever print something, that means we've proven it. We've proven the thing. Okay. So let's see, what do I want to do next? I think, yeah, let's run it. I've hyped it up so long. Let's watch it in action. We accept. That's funny. And so there it went. Cancel. So there. All it was is it printed 53. But all these things were working together. Look at them. So we started at 51. 51 must have not been prime because otherwise we would have printed it and stopped. Then we made I52. 52 is obviously not prime. That we didn't hit that. We made I53. And now we checked if 53 was prime, and this gave back true. Apparently, try all the possible factors from 2 to 50. It gave 2 to 52. It gave back non-zero remainders each time. And so we got to this part, and it gave back true. And that means we hit the body of our if, print our I of 53, and stop our program. So we don't have to keep going. And so this output right here, if you look at the program and you think about it, scratch your head long enough, this is a proof. This is our value for x, right? This is a number bigger than 50 that is prime, and that proves that this proposition is true, that statement was a true statement, which is kind of magic. Any questions about that? It's pretty cool. I'm a fan. So there's a huge correspondence between programs and proofs. This is like your just the tip of the iceberg, I would say. But yeah, that's a key idea. Like we don't have to learn a lot of math. We can just like write a program to search for an answer, and if we find it, that means we've proven something. Okay. At least for something like a there exists, right? Because for a there exists, it's just like you got to find one good one. And that's easy if it is a true statement. Okay, so yeah, with that in mind, let's see, what do I want to do next? Let's do one more proof. Let's do it for all this time. Let's prove that for all integers, call them n, between 0 and 100, the square root of n is less than or equal to 10. That's a true statement, right? I think. Because, like, square root of 0, it's totally 0. And then the graph of square root looks like this, right? The square root of 100 is exactly 10, right? So I think that should check out. Any bigger, though, it is bigger than 10. Does that make sense? So that's what we want to prove now. So we're gonna follow our strategy that we've been doing, especially the one that we did for this one. All right, let's figure this out together. So we want to prove that for all integers n between 0 and 100, the square root of n is less than 10, or less than or equal to 10. And so we have to make math out of this first. So let's figure that out. Do you see there's a for all here for sure? What else do we need here? All right. How do we talk about the range too? Like how do we figure that out? So okay, let's convert it to mathematical English. This is a little bit better. Do you see how this is the same thing? It's like you give me an n. This is it picking out the range. You see how this picks out a range? Like if that number, if n is bigger than or equal to 0 and it's less than 100, then this is true about n. Does that make sense? That's better. That's closer to math, isn't it? And that plops out the range for you too. It's like, if this is not true about n, I don't care about its square root. I don't care about comparing it anymore. It's like if it's negative or it's bigger than 100, like that's not part of the thing that I care about. Only if this is true about n, is it within the range that I want to check something. See that? That's nice. That's what I want there. And then, like if that's true, if n is within the proper range, then I want to check that this is true for n. Okay, so that's still corresponding to the original statement, right? I hope you see that. And this is closer to math because if and then, those make up our implication, right? So that's useful. That's what we want to see there. That's our mathematical if-then statement. And so let's convert that to math. Let's replace this, right? And we have like an and. Let's make that the thing that it should be, right? Our logical and statement. So if we convert this to full-blown math, it looks like this, right? If n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n is less than or equal to 10. And so this is what our if-then becomes. And then also, I kind of got rid of a little bit. I got rid of the for all part, haven't I? This right here, like you give it an n, it gives you back true or false. But you need to fill in the n right now. It's neither true nor false right now. So it's a predicate again. It's something with a variable. And so I want to prove that this predicate is true for every n, right? Don't I? Every n under the sun. Because like, if this isn't true about n, like it's automatically true based on the truth table for implication. So we're going to add in the quantifier now to create a proposition that we can then prove true or false. Okay? So just plop in the quantifier right here. It's the one that you would expect for all integers n. For all n values, if this is true about n, if it's greater than or equal to 0 and it's less than or equal to 100, so within the range I care about, then it better be true that the square root of n is less than or equal to 10. See that? So that is everything I wanted. And this is now a proposition that I could then go prove true or false. Okay. So going back to very precise English, hopefully, like you caught me as I said it, but like this statement above and this math right here, those are saying the same thing, all right? Precisely what this is saying is like for all n, if n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n is less than or equal to 10. Which is just a flowery way of saying exactly this, but now it's completely specified. All right? Are there any questions about that translation? Does it make sense why we got from there to there? The bit about the range is kind of weird. I'll give it that, but that's kind of how you pick out a range in mathematical terms. It's like, this better be true about it. Better be between here and here. So like greater than this, less than that. So what I'd like you to do now, I'll give you a chance to try it. Okay? So we've got our proposition. Here's like this is something you can prove true or false, right? So do it. Try it. I'll give you 5 minutes. We got plenty of time. Take what we just talked about and make a program, or at least write some pseudocode up. You don't have to submit this anywhere, but like here's our relevant code from last time that was searching for stuff. Take this and maybe modify it. Do you see how you could prove even a for all true, right? Because it's just a range. See if you can figure out how to make a program that proves this formula to be true, because it is a true statement, right, based on the graph that we drew. Can you write a program that makes sure this is true? Like prints out yes, it's true, or prints out no, it's not. Like what would you have to search for? You have to use some if statements for sure. There's a range of numbers that are relevant, right, that you care about. Could you do that? To get the square root, by the way, that's the math library, import math. You got to do import math. And then you'll say math.square root of like 2, for example. So like that's going to give you your square root. But yeah, do you kind of see how you do it? I want to give you a head start. So take some time, give this a try. Open up idle and let me if you have any questions. But you see how even though it's a for all, it's for all numbers between here and here. numbers and make sure, always, without a doubt, this holds for all those numbers, right? We want to make sure this is true for all those numbers. Assume that n can only be an integer. That will make it easier on you. Don't try every possible float in between. That would be hard. So just like checking for primes, you can break out early and be like, and be done with the thing when you notice a bad number, right? You can stop early if you notice something wrong, and like it's immediately false if something doesn't work out because it's supposed to be true for everybody. But you have to wait until the end to claim that it's true, right? You have to try every possible number before you are convinced that it did the right thing for all of them. Another minute or so, then I'll show you my answer. All right. Give me 1 second. Did any questions come up as we were trying to make enough sense? So let's see. How would I don't want to do this with you. So yeah, let's figure this out together. So prove that for all numbers n between 0 and 100, the square root of n is less than or equal to 10. So we got this idea, this proposition back to us, and now we have to prove it to be true. So kind of what we want to do is like go through all the numbers, right? Try n being 0, n being 1, n being 2, all the way to n being 100, and like take their square root, right? Take the square root of 0, take the square root of 1, take the square root of 2, all the way to the square root of 100. And like each time I get a number, I better make sure it's less than or equal to 10, right? If there is ever one that is bigger than 10, then I can immediately say, no, this didn't work out, right? And the thing's false. But if they all are okay, they're all fine, that means then it is true for all of them. We gotta wait until the end, right? Can't just try square root of 0 and be like, oh yeah, it works for all the numbers between 1 and 100. You gotta try them all. Okay? So as far as English-looking code goes, pseudocode, what we want to do is we want to loop through every number, call them n between 0 and 100, and we'll check and see. Like, if the square root of that number is greater than 10, I'm done. Stop and print false, like stop the program. It's a false theorem. Otherwise, see, I'm checking the opposite thing here. That's useful. That's important. That's helpful here. Because otherwise, if it was true, it's like I just got to keep going. And so, like, you can just keep that implicitly, not have to worry about it. But that's your loop. If the loop ever finishes without complaining, that means they all worked, right? Nobody was a bad one. So if you got through the entire loop, you got down here without ever shouting out that it was false, then we can print true. Does that strategy make sense? And that will prove that every number between that range, it all works out. And that's our theorem. That's perfect. So let's see if it works. I'll make a new file, and I better import the math library this time. So yeah, well, let's see if I can get this on the same page as the text here. Something like that. So, okay, so I want the math library, and what I want to do is I want to have an n variable, right? I want an n variable. I guess you can call it anything, but I'll start at 0. I'm going to have it range up to 100. While n is less than or equal to 100, do some stuff, check things, and then n equals n plus 1 to try the next one. So this will range, n will now range and run the body between 0 and 100 exactly. All right, so what do I want to do with each n? I want to check it each time. I want to make sure that the square root of n is less than or equal to 10. So if it's ever bigger, I want to give up and say no. So if calling math.square-root on n is ever bigger than 10, then I found a counterexample to my theorem. I found an n value that is not less than or equal to 10. So I'll say print false. And just like I can stop the program, it's no use to try any more n values because like it's already false. Yeah. Otherwise, if we're still going, it checked out still. I want to try the next one. I want to make sure it all works out. Right? So that's all that. So this loop will run, hopefully, to completion. It's just checking every one of those guys, making sure the square root is within the right range. So if we haven't given up, the loop will range, having n go from 0 to 100, and it will finish. And if it ever finishes without complaining, because like if we ever get down here, that means we didn't call quit, because quit just stops the program and doesn't do anything else. So if we got down here, that means the theorem was true. So if we ever get here, the statement must have been true. So we'll say that. True. Okay? So that is going to be our little program there. And so if I run this, well, I got to give it a name first. Let's call it square root proof.py. If I run this, it's going to try all those numbers and does it very quickly, and it prints true. So all of them, every number between 0 and 100 really was less than or equal to 10 because it didn't trip this if statement, and it printed true because it got through them all. Any questions about that? Do you see how that proved our proposition here once and for all? That's pretty cool. We can write a program that proves a mathematical theorem. I like it. I'm a little biased, though. So, yeah. Any questions about that? I think that's the meat of today. All right. So, yeah. Let's say that our theorem was false. Like, here's a false theorem. Let's be like, prove that for all numbers between 0 and 101, right? Square root of n is less than or equal to 10. This is a false theorem, right? Not just everything that you write in math is true. This is not true now if we change it to that. So we have to loop now between 0 and 101, and we all know that the square root of 101 is going to be bigger than 10. And so that's going to get to this statement. Square root n will be 101. It'll have a chance now. Square root of 101 is totally bigger than 10, just a little bit though, and it'll print false and stop the program. So that's disproving our theorem now if we made a bad theorem. It was wrong. If we went to 101 instead. Okay? That's the idea there. And so I hope that makes sense to you. This is like a math problem, and we found that it worked out for the first one and didn't work out for the second one. That is a valid kind of proof technique. It's very cool. So yeah, I guess the moral of this story is like logic, this thing we've been learning on the side. Like, sure, it's useful when we're making if statements and stuff, but like, it's just everywhere in computer science. Logic and computer science, so much better together. So we love logic, we love computer science, hopefully. And yeah, the idea is that like, you don't write a program and just like turn off your brain, do you? You have to like reason about things logically. You have to use your logical ideas and truth tables that we learned about. That makes your life easier. If you use both while you're writing, you're usually going to make a better program that is correct more quickly, right? So using both together helps you write correct programs, and it also helps you prove to yourself, at least in your mind, if not on paper, why the ones that you've written are correct. And it helps you track down bugs, right? If you think logically, like, okay, what value must have messed this loop up? There's a lot of logic going on when you're thinking about your programs day to day as a computer scientist. So yeah, I think that's all that I wanted to say. Trying to poison your minds, get you to think about logic plus programming. So it's a nice crossover lecture for the day, I think. So yeah, if we are good, the last thing that I want to talk to you about is your next programming assignment, since you also have one due for those this week. This will also be due week 14, so you get 2 weeks to do it. And so this will be referencing the last major programming lecture. That was the one where I was drawing random stuff. So I would like you to make a program that draws a bunch of random squares and triangles, right? Because I know you know how to do that too. So here is the setup. Here's the program I want you to write, okay? I want you to ask the user for a number, and I'll use n. You could call it whatever you want, but I'll say n for the rest of these instructions at least. So like, let's say the user types 100, or they type 50 or something, all right? So let's say they type 100. So n is 100. You got that from the user. Could be different every time, though. And so you have to do the following n times, all right? Using a while loop or a different kind of loop if you know how. So you want to repeat the following to draw n shapes, okay? Your goal is going to be, each shape will be a different color, so I want you to set the color for the shape you're about to draw to be random, like I showed you in class. There's plenty more colors where that came from, like I just gave you the rainbow. Here's like a huge list of every color that Python supports. All these bad boys. Amazing. So feel free to use them. Use the fancy colors if you'd like. Randomly pick a color, and then also randomly pick whether you're about to draw a square or a triangle. Because I want you to draw some squares and some triangles that should be random, like you're flipping a coin every round to see if I'm about to draw a square or I'm about to draw a triangle, okay? So my hint for you there is like, pick a number between 1 and 2. Like if it's 1, go and draw a square right now, or if it's 2, go and draw a triangle right now. That's the goal. So like when your program runs, it should draw some squares and some triangles. The total number of shapes you're drawing will be n, but it's random how many squares and triangles you do. Yeah, because you're like flipping a coin every round, okay? So then you also need to pick a random size for your square / triangle, and then draw it with that random color at that random location. Okay. Does that make sense? So n shapes total is what you're going to draw. The user's telling you how many shapes they want. So you're going to repeat this n times, and you're doing most of what I did for the square drawing stuff, but it could also be a triangle. This bit is kind of the harder bit. Okay, so you have to like flip a coin every round inside of your loop. Am I about to draw a square right now, or am I about to draw a triangle right now? And my hint to you, the way that I think you should do it, is just generate a random number between 1 and 2. If it's 1, do the triangle. If it's 2, do the squares. Okay, does that make sense? That's going to be the secret for that. And so, like, don't draw, like, if these are types 50, don't draw 25 squares and 25 triangles. Like, I'd hard code that. Make it so that it's random. Like, sometimes you draw, like, I don't know, 33 squares. Sometimes you draw 22 triangles. I don't know. Whatever adds up to 50. It's just random every time. You're flipping a coin every time you want to draw a shape. Okay? So end shapes total. You can go back to my code from class for the random squares. That should help you with a lot because I was using a random color there. But yeah, just that's the program I want to see. And give me a video as usual. Walk me through your code. Show me what's going on. Show me it running. It's very satisfying to get it working, I think. So this will be due in 2 weeks. And you're drawing random squares and triangles of random colors and locations of a number of the user's choosing. So I think that's everything I wanted to say. Any questions about any of that? All right, that is officially all that I have for us today. So you're welcome to get started if you'd like.